Module 2, Lecture A, Decisions and Loops. By the end of this lecture, you will be able to use conditional statements to evaluate electrical design limits and safety thresholds. Write loops that repeat calculations across component values, frequencies, or time samples. And combine decisions and loops to search for values that satisfy engineering constraints. Safety limit checks. Current limit checks. Current limit checks help keep electrical design safe by comparing expected current with each component's rated limit. Conditional logic can flag unsafe conditions, such as currents that could overheat a trace or damage a part. If the current is within the safe range, the design can proceed. If not, the engineer must adjust the component, widen the trace, or stop operation. When checking current limits, engineers must account for the difference between ideal calculations and real circuit behavior. Surges, transients, motor startup current, and capacitor charging can cause brief current spikes that may still be acceptable. Conditional logic helps distinguish these temporary inrush currents from true overloads, allowing short spikes while shutting down if high current continues. This is part of a broader safety approach that considers timing, operating mode, and the consequences of failure. Current limit checks are essential when designing automated tools for evaluating circuits. By testing different resistor values, voltages, and load conditions, software can flag unsafe current levels before hardware is built or deployed. This is especially important in systems like power distribution and robotics, where loads can change suddenly, such as when multiple motors stall. Integrating these checks into design tools and firmware helps protect systems from electrical overload. Python code. Current limit checks. Always compare current levels with the component ratings to ensure the design stays within safe limits. Conditional statements help enforce this safety logic, and using small examples makes the rules easier to understand. The system defines 3 expected current levels for safety comparison: 1.8 amperes during normal operation, 3.4 amperes at startup, and 6.2 amperes during a fault. These values represent typical use, the initial power-on surge, and a fault condition, helping verify that the system stays within safe limits. The system sets 2 current safety limits: a continuous limit of 2.5 amperes for sustained operation, and a short surge limit of 4 amperes for brief transients such as startup. It then announces that a current limit check is beginning. The system checks whether the normal operating current stays within the continuous current limit. If it does, continuous operation is marked safe. If not, it is marked unsafe. This helps prevent operation beyond the system's design limits. The system checks whether the startup current stays within the safe short surge limit. If it does, the surge is marked acceptable. If it exceeds the limit, it is marked too high. This ensures brief current increases remain within what the system can safely handle. The system compares the fault current with 2 safety limits. If it exceeds the short surge limit, it shuts down immediately to prevent damage. If it is below that limit but above the continuous limit, the load should be reduced or the current limit adjusted. If the current stays within both limits, no immediate action is needed. The code reports whether normal operating current, startup surge current, and fault current are within safe limits. It uses clear printed messages to show when current is safe, acceptable, manageable, or requires immediate action. It then recommends choosing component ratings above the worst credible current to improve safety and reliability. This script compares current levels with safety limits for normal operation, startup, and fault conditions. Normal current must stay within the continuous limit, while startup current is checked against a short surge limit. For fault current, exceeding the surge limit calls for immediate shutdown, while exceeding only the continuous limit suggests reducing the load. These checks help guide component ratings for the worst credible current scenario. Voltage limit checks. Voltage limit checks help ensure electrical components stay within safe operating ranges. A program compares actual voltages with allowed limits, then either continues operation or responds with actions, such as warnings or disabling outputs. This turns design rules into clear decisions that can prevent component overstress before hardware is built or deployed. Voltage checks in engineering must account for real-world changes, not just ideal ratings. A supply can rise or fall with charging and load, and sensitive electronics need protection from unsafe levels. By using conditional logic, systems can recognize normal variation, warn when voltage approaches limits, and shut down when a fault could cause damage. Voltage limit checks help keep electrical systems safe and compliant by preventing components or signals from exceeding their allowed ranges. If limits are exceeded, insulation, control circuits, or other parts can be damaged. Using conditional logic, engineers can build safeguards that classify voltage levels as acceptable, uncertain, or unsafe based on the system's requirements. Python code, voltage limit checks. Conditional checks help protect voltage-rated components by classifying the measured supply voltage. Safety margins then support better engineering decisions. We store the measured voltage values in a list, so they can be checked against safety limits. This structure makes it easy to review each value systematically. The system uses 12 volts as the nominal expected voltage level, and 15 volts as the maximum safe limit. These values define the normal operating target and the upper safety boundary for judging measured voltages. Set a warning threshold at 90% of the maximum voltage to give an early alert before the safe limit is reached. We loop through the voltage measurements and use the enumerate function to match each value with its sample number, starting at 1. This makes it easy to work with both the position and the voltage value for each sample in an organized way. The code uses conditional checks to classify a voltage level against safety limits. If the voltage is too high, it reports a fault and indicates the output should be shut down. If it is close to the limit, it reports a warning. Otherwise, the voltage is treated as safe and within the acceptable range. To find the safety margin below a maximum voltage rating, compare the current voltage with the maximum allowed voltage. The difference is divided by the maximum rating and converted to a percentage. This shows how much room remains before the voltage reaches the safe limit. For each voltage sample, the code prints a short summary showing the sample number, the voltage, its safety status, and the safety margin percentage. The numeric values are rounded to 1 decimal place, making the output easy to scan and compare against the safety criteria. The code prints a brief safety message about the voltage limit. It states that the system is safe when the voltage stays at or below the maximum allowed value, clearly reinforcing the acceptable operating range. This script checks measured voltages against safety limits and reports whether each one is safe, near the warning threshold, or in a fault condition. It also shows the percentage margin below the maximum allowed voltage. The key rule is that voltages at or below 15 volts are considered safe, giving a quick summary for engineering safety assessment. Power limit checks. Power limit checks help keep electrical components within safe operating ranges by comparing calculated power to design limits. Even if voltage and current seem acceptable, parts like resistors or transistors can still overheat, especially during startup or fault conditions. In programs and controllers, conditional checks can trigger warnings or reduce load, helping prevent damage and safety hazards. Checking power limits requires more than comparing a value to a rated maximum. Real conditions such as temperature, airflow, space constraints, and whether power is continuous or brief can change what is safe. Conditional rules help capture these limits by separating normal operation from overload conditions. In practice, safety thresholds must reflect the device's real operating context, not just its theoretical rating. Power limit checks help real systems protect hardware and users. Devices such as battery managers, lab power supplies, and audio amplifiers can reduce or shut off output when demand, heat, or other conditions become unsafe. In design analysis, programs use these checks to test operating points and avoid power violations, supporting safer and more robust designs. Python code, power limit checks. Before accepting a circuit's operation, confirm that each resistor's calculated power is within its allowed limit. Use simple condition checks to compare the power values against those limits, and keep any supporting tables small so the example remains easy to follow. We define a set of resistor values from 100 to 1000 ohms and a set of applied voltages from 3.3 to 12 volts. We also set the maximum safe power at 0.25 watts. Together, these values let us check whether each resistor can safely handle each voltage condition. The script starts by introducing that it will check power limits for quarter-watt resistors. It then prints a clear table header with columns for resistance, voltage, calculated power, and the resulting decision, so the later results are organized and easy to read. The process pairs each resistor with its voltage, then calculates the power dissipated by dividing the voltage squared by the resistance. It compares that power to the resistor's rated limit by converting it into a percentage. This shows how close each resistor is to its maximum safe power level. The code assigns a safety status by comparing the calculated power to the power limit. If the power is at or below 70% of the limit, the status is OK. If it is above that but still within the limit, the status becomes warning. If the power exceeds the limit, the status is over limit, meaning it is unsafe. The code prints a formatted summary of each power limit check. It shows the resistor value, voltage, calculated power, and final decision in a consistent layout, making each resistor and voltage result easy to read and compare. The code sets a safe margin at 70% of rated power, meaning usage below that level is considered safe. It then creates and prints a brief summary explaining that an OK result means the power use stayed under this threshold. The script checks whether 4 resistors can safely handle their assigned voltages without exceeding a quarter-watt power limit. It calculates each resistor's power as voltage squared divided by resistance, then labels the result as safe, warning, or over limit based on how close it is to the limit. The output reports the resistance, voltage, power, and decision for each case, along with a brief note on the safety margin used. Loop patterns. For loops. A for loop is used to repeat a calculation when the number of repetitions or set of values is known. In engineering, it helps apply the same process consistently across components, frequencies, or data points, such as checking voltages or filter responses. The loop defines which values to use, what calculation to repeat, and how to store or use the results. In a for loop, each pass through the loop is an iteration that applies the same logic to the next item in a sequence. This is useful in design studies and simulations because it lets you test a relationship across many conditions. For example, frequency response analysis can check circuit gain and phase over a range of frequencies, giving a broader view of performance while reducing human error and keeping the analysis consistent. A well-designed for loop helps engineers test a series of cases in a clear, consistent way. By varying values and repeating the same analysis, designers can compare options, identify trends, and find limits. This pattern supports tasks such as parameter sweeps and simulation-based design, where organized iteration guides better decisions. Python code for loops. Use for loops to test different resistor choices by repeating the same circuit calculation in a systematic way. Keep the printed results brief so the output stays easy to read in Colab. We set the circuit's supply voltage to 5 volts as a constant reference for all calculations. Defining it once at the start keeps the calculations consistent and makes the code easier to understand and maintain. A list of resistor values in ohms stores the circuit options to evaluate. Keeping them together makes it easy to repeat the same calculations for each resistor value in an organized way. Begin by creating an empty list to store the calculated current for each resistor. This prepares the program to collect each result as it loops through the resistor values. For each resistor, the current is found by dividing the fixed supply voltage by the resistance. The result is then converted from amps to milliamps by multiplying by 1000. Each milliamps value is stored in the results list for later use. The code prints a short header introducing a resistor sweep for a 5-volt source. This tells the listener that the results will show how changing resistance affects current in the circuit. The resistor values are paired with their calculated currents using the zip function, so each result can be reported together. For each pair, a clear message is created showing resistance in ohms and current in milliamps rounded to 2 decimal places. Printing these messages makes it easy to compare each resistor with its corresponding current. To summarize the loop results, we find the lowest current value from the calculated currents using the minimum function. This gives the smallest current tested during the resistor sweep, which is then displayed rounded to 2 decimal places. This script compares currents through several resistors connected to a 5-volt supply. For each resistor, it calculates the current in milliamps, records the result, and presents a compact comparison of resistor value and current. It also reports the lowest current, showing how higher resistance reduces current in a simple circuit. While loop patterns. A while loop is used when a calculation should continue until a condition changes, rather than for a fixed number of repetitions. It keeps running while a logical test is true and stops when that test becomes false. This is useful in engineering processes that depend on reaching a target state or tolerance, such as a voltage threshold or stable temperature, when the number of needed iterations is not known in advance. A well-designed while loop starts from an initial value, repeats a calculation, and updates the value being tested so the loop can eventually stop. Planning the stopping condition is essential because without a clear endpoint, the loop may run forever. In applications such as frequency sweeps or battery discharge calculations, Each pass must deliberately change the relevant quantity, making the loop easier to understand, verify, and control. While loops are useful when a calculation should continue only until a design goal, safety limit, or stability condition is reached. In engineering, they can guide adjustments such as tuning resistance, reducing sensor error, or running a simulation until the result settles. Effective use depends on clear stopping conditions, sensible step sizes, and limits that prevent unsafe or unhelpful calculations. Python code. While loop patterns. While loops keep repeating until their condition changes. In electrical simulations, they are often used to stop a process once a threshold is reached, while safety guards help prevent loops from running endlessly. To simulate a capacitor charging circuit, we define three key constants: a 5-volt supply, a resistance of 10,000 ohms, and a capacitance of 1/10,000th of a farad. Together, these values determine how the capacitor charges over time. The simulation is set to stop when the capacitor reaches 3.2 volts. It updates the voltage every 0.05 seconds, and a limit of 500 steps prevents the loop from running indefinitely if the target is not reached. The simulation starts by setting its initial conditions. Time begins at 0 seconds. The capacitor voltage starts at 0 to represent an uncharged capacitor, and the step count begins at 0 to track loop iterations. These values provide the baseline for modeling the charging process over time. The loop runs until the capacitor reaches the voltage threshold or the maximum number of steps is reached. Each iteration computes the charging rate from the gap between the supply voltage and the current capacitor voltage, scaled by resistance and capacitance. It then updates the capacitor voltage, advances the simulation time, and increases the step count. The step count increases by 1 each time the loop runs. This tracks how long the simulation has been running and helps stop it from exceeding the allowed limit. It also prevents the process from getting stuck in an infinite loop if the voltage threshold is not reached. The code identifies why the simulation ended by checking the capacitor voltage. If the voltage reached the threshold, it records that as the stop reason. If not, it records that the simulation stopped because it reached the maximum allowed number of steps. The simulation prints a concise summary of a capacitor charging while loop. It reports why the loop stopped, either because the target voltage was reached or the step limit was hit, then shows the elapsed time, final capacitor voltage, and total number of iterations. These outputs help confirm the result and give a quick sense of the loop's performance. This script models a capacitor charging in a circuit using a while loop. Each step updates the voltage based on how far it is from the supply voltage, scaled by the resistance and capacitance. The loop stops when the target voltage is reached, or a maximum step count prevents it from running forever. At the end, the script reports why it stopped, along with the elapsed time, final voltage, and number of iterations. Resistor iteration. Resistor iteration is a common loop pattern in electronic design that tests a range of standard resistor values against a desired circuit behavior. Instead of choosing an ideal value in isolation, engineers compare practical options to see which ones meet the design needs. This helps narrow the choices before buying parts or building prototypes, making the design process more systematic and efficient. Resistor iteration is a systematic way to compare resistor choices and see how each one affects a circuit. It can help verify safe LED current, maintain brightness, or find voltage divider values that fit an analog to digital converter's input range. Repeating the calculations consistently reduces errors and reveals trends that a single trial might miss. Resistor iteration helps engineers evaluate a component in the full design context, not just by its nominal resistance. Loops can test variations such as tolerance, power limits, temperature effects, and supply voltage changes. This makes it easier to choose safe, reliable parts and connect circuit theory with practical engineering decisions. Python code, resistor iteration. Loop patterns help compare practical resistor values by testing each option in the same way. This makes it easier to identify choices that are both safe and useful. The LED circuit is defined by 4 key limits: a 5-volt supply, a 2-volt drop across the LED, a minimum operating current of 5 milliamps, and a maximum safe current of 20 milliamps. Together, these values set the required voltage and current range for designing the circuit safely. The program defines a set of standard resistor values to test as possible LED current limiters. It prepares a place to store the values that meet the safe operating criteria, then prints a console header showing that each resistor will be evaluated by its resistance, resulting current, and decision outcome. For each resistor value, calculate the circuit current by taking the supply voltage minus the LED voltage and dividing by the resistor. Convert that current to milliamperes, then check whether it falls within the allowed minimum and maximum range. If it does, the resistor is suitable for the circuit. The code tests whether the resistor current stays within the allowed range. Resistors that meet the limit are marked acceptable and added to the safe options, while those outside the range are rejected. This helps identify which resistors are suitable for the LED circuit. The code prints a short summary for each resistor option, including its resistance, the calculated current in milliamps, and the final decision label. This makes it easy to compare how each resistor performs in the LED circuit. After checking the resistor values, the code determines whether any safe options were found. If so, it chooses the first acceptable resistor. If not, it records that no value is available. It then creates and prints a short summary stating the selected resistor value in ohms. The script tests different resistor values to find safe choices for limiting current through an LED. For each resistor, it calculates the LED current from the supply voltage, LED voltage, and resistance, then converts the result to milliamps. It accepts resistors that keep the current between 5 and 20 milliamps, reports each result, and finally prints the first safe resistor or notes that none are suitable. Constraint searches. Threshold search. A threshold search finds the point where a design condition changes status, such as becoming safe or acceptable. Instead of only calculating a value, it tests values until a critical boundary is crossed, like the smallest safe resistor or the first frequency where output falls below a limit. The basic process is to try a value, check the constraint, and stop once the threshold is reached. A threshold search tests possible values in an organized way until an engineering limit or target condition is reached. For example, it can identify the voltage needed for reliable circuit operation or the load current that causes overheating. A loop checks each option, while a conditional statement detects when the constraint changes. This approach is useful when many values must be tested, or simulation results need consistent evaluation. When designing a threshold search, choose the step size, stopping condition, and final interpretation carefully. Larger steps are faster but less precise, while smaller steps improve accuracy with more computation. A good stopping rule prevents endless searching or stopping too soon, and any result that meets the constraints should still be checked with appropriate safety margins. Overall, Threshold search combines repeated calculation with engineering judgment. Python code. Threshold search. A threshold search uses a loop with a decision to find the first value that meets a condition. In this example, it checks whether capacitor ripple stays within its limit and stops as soon as it finds a successful case. Set the key capacitor design values. The load current is 0.08 amperes. The AC frequency is 120 Hz. And the maximum allowable ripple voltage is 0.10 volts. These values define the current demand and the ripple limit the capacitor must stay within. We begin with a set of common capacitance values in microfarads as candidates for the threshold search. The process also starts with empty placeholders for the selected capacitance and its ripple voltage, meaning no suitable capacitor has been found yet. This prepares the search to test each option against the required ripple voltage limit. The process checks each candidate capacitance value by first converting it from microfarads to farads. It then calculates the ripple voltage as the load current divided by frequency times capacitance. The loop stops when it finds a capacitance that keeps the ripple voltage at or below the allowed maximum. The code compares the calculated ripple voltage with the maximum allowed value. If it is within the limit, it saves the current capacitance and ripple voltage as the selected values. This means a suitable capacitor has been found, so the loop stops without checking further options. The code performs a threshold search for capacitor ripple by showing the key inputs and candidates being tested. It reports the maximum allowed ripple voltage and the load current, both rounded to 2 decimal places. It also displays the capacitance values evaluated, making it clear which options were checked against the ripple limit. The code reports whether the capacitor search succeeded. If no listed capacitor meets the ripple limit, it prints a failure message. Otherwise, it shows the first acceptable capacitance in microfarads, along with its estimated ripple voltage, rounded to 3 decimal places. The script searches for the smallest capacitor that keeps ripple voltage within the allowed limit. It checks candidate capacitance values in order, calculates the ripple from the load current, frequency, and capacitance, and stops at the first value that meets the limit. It then reports that capacitor and its ripple voltage, or says that no suitable capacitor was found if none qualify. Filter feasible values. Filtering feasible values means checking each option against all required conditions and keeping only the ones that pass. In engineering, a component or design often must satisfy several constraints at once, such as electrical limits, timing, tolerance, or size. Loops can test each candidate, while conditionals decide whether it should be accepted or rejected, much like a design review. In large or repetitive design spaces, engineers can save time by filtering candidate parts to find feasible choices first. They estimate key performance measures for each option, such as voltage or heat, and remove any candidate that violates required limits. This separates identifying safe, workable solutions from later choosing the best one based on goals like cost or reliability. This technique makes design decisions clearer and more repeatable by applying constraints consistently. It helps designers separate hard safety limits from practical limits, then filter out infeasible options before making a final choice. The result is a more disciplined workflow that reduces errors, improves safety, and makes designs easier to adjust when requirements change. Python code, filter feasible values. Search possible resistor values by checking them against each design limit, and keep only the values that satisfy all requirements. This reflects a practical filtering process for electrical feasibility. For this LED circuit, the 5-volt supply provides the total available voltage. Since the LED drops 2 volts, the resistor must handle the remaining 3 volts. The current limit is set to 20 milliamps to keep the LED operating safely. The circuit design sets a minimum LED current of 10 milliamps to ensure proper operation and limits resistor power to 125 milliwatts to prevent overheating. The available standard resistor values range from 100 to 470 ohms, and these will be checked to find the options that satisfy the design requirements. Create an empty list for resistor values that meet the circuit requirements. Then check each standard resistor by finding the voltage across it, using the supply voltage minus the LED voltage drop. This prepares each resistor to be evaluated for safe and effective use in the LED circuit. The code finds the resistor's current by dividing the voltage across it by its resistance, then calculates the power it dissipates by using that current and the resistance. These values show whether the resistor is operating safely and effectively. The code determines whether a resistor is feasible by checking 3 limits. The current must stay below the maximum safe value, meet the minimum useful value, and keep power dissipation within the resistor's rating. Only resistors that satisfy all of these safety and performance conditions are accepted. This code checks each resistor against the required current and power limits. If the current is within the useful and safe range, and if the power dissipation stays below the safety limit, the resistor is treated as feasible. Its current and power values are then saved for later comparison. The output begins with a header introducing the feasible LED resistor values. The program then goes through each resistor entry, which includes resistance, current, and power. For readability, it converts current from amps to milliamps, a more familiar unit for typical electronics work. For each usable resistor value, the code reports the resistance in ohms, the current in milliamps, and the power dissipated in watts. This gives a quick way to compare resistor options and understand their basic performance. The process selects a preferred resistor by choosing the first option from the feasible list. If no feasible resistor exists, no choice is made. The selected resistor's value is then printed as the preferred option, giving a simple way to identify a suitable circuit component. The script checks standard resistor values to find a safe choice for an LED circuit. For each resistor, it calculates the LED current and power, keeping only options that produce 10 to 20 milliamps and stay below 0.125 watts. It prints the feasible choices, then selects the first one as the preferred resistor. Valid value search. A valid value search uses a loop to automatically test possible settings until it finds ones that meet engineering constraints. In electrical design, this can help choose components such as resistors or capacitors that satisfy limits like safe current or timing behavior. The loop handles repeated testing, while decision logic determines which values are acceptable, making the process systematic instead of trial and error. A valid value search checks more than whether a value is mathematically possible. In engineering design, each option must also satisfy practical limits for safety and performance, such as current, power, voltage, signal size, clipping, and noise. Only values that meet all required conditions are accepted, helping produce precise and reliable designs. A valid value search helps engineers choose practical design values from real component catalogs. If only a safe operating point is needed, the search can stop at the first acceptable candidate. If optimization matters, it continues to find the best value for goals such as lower power loss, lower cost, or higher noise margin. Python code, valid value search. The process searches standard resistor values to find safe loading conditions. Each candidate is checked against current and power limits before a suitable choice is accepted. No extra packages are required to run the script. It uses only Python's built-in features, so it can run easily without installing external dependencies. We first define the standard resistor values available for the circuit tests. This creates the set of options the code will later compare against the required electrical constraints. Set the supply voltage to 5 volts, which is applied across the resistors. To ensure safe operation, keep the current at or below 25 milliamps and the power at or below 125 milliwatts. Any selected resistor must stay within these limits to avoid unsafe current flow or overheating. Begin by creating an empty list to hold the valid resistors. As each resistor is checked against the current and power constraints, only those that pass are added, making it easy to track the suitable options. For each standard resistor value, calculate the current by dividing the supply voltage by the resistance. Then calculate the power by multiplying the voltage by that current. These results show whether each resistor stays within the required current and power limits. The code filters resistors by checking whether each one stays within its allowed current and power limits. Only resistors that meet both safety constraints are added to the valid list, along with their calculated current and power values. To choose the best resistor, first check whether any valid options exist. If the list is not empty, select the first resistor, assuming the list is sorted, so this is the lowest resistance that satisfies all constraints. If no valid resistors are available, the best choice is none. The code prints a brief summary of a search for valid load resistor values at 5 volts. It reports how many standard resistor values were tested and how many met the required constraints. This gives a quick overview of the resistor selection results. The process first checks whether a valid resistor choice exists. If one is found, it reports the first acceptable resistance value, along with the corresponding current and power converted into milliamps and milliwatts. This gives a concise summary of the resistor that satisfies all required constraints. If no resistor matches all the required conditions, the program tells the user that no suitable option was found. This makes the result clear and prevents confusion about the search outcome. The code prints a concise list of resistor values that meet the required constraints. It does this by taking the resistance value from each valid resistor entry and collecting those values into a new list before printing it. The script checks standard resistor values for use with a 5-volt supply, allowing only those that keep current at or below 25 milliamps and power below 125 milliwatts. It records all valid choices, selects the lowest valid resistance as the best option, and reports its current and power. If none qualify, it tells the user, then summarizes the valid resistor values found. In this lecture, you learned to use conditional statements to evaluate electrical design limits and safety thresholds, write loops that repeat calculations across component values, frequencies, or time samples, and combine decisions and loops to search for values that satisfy engineering constraints. In the next lecture, Lecture B, we will go over functions and modules.
Thank you for your attention. See you all in the next lecture.